what's up, YouTube? So if you join it in, we're just gonna be looking at a couple of papers, at a couple of journals. While I try to get ready for the day. It's like 7 something, and I have to get up at like 9. But we need to really take a look at these papers and see what they're talking about. So we're just gonna like reviewing a couple of papers and stuff. So, I do have some chicken in the oven because you gotta meal prep and stuff. But I do have something in the oven, so I will like take breaks once in a while, go check on it. I don't want the item to burn and go to waste. But the goal today is to read a paper on catalysis. I think I'm just gonna settle on the catalysis paper. And so if you're joining in from last time, we kind of came. We were just scouring around the Nature journal, Nature Catalysis journal, and I think I found something that I wanted to read. So I'm gonna get my bag. My bag. Found a couple of things I wanted to read. Oh damn, it's not here. So I do know what I'm going to read. Oh, it's right here. Yeah. So. All right, let's do this. Let's do this about that. All right. Shout out Epidemic Sound for the free papers. Right. Okay. So neutral photo-generated end-centered radicals as general catalytic direct hydrogen atom transfer platform for aliphatic CH functionalization. And then there was something on beta lactams. Right. So. Selective CC bond cleavage enabled emulation between beta lactams and pi systems via a nickel aluminum bimetallic catalysis. Now I don't have access to the full journal. I got access to my institution, so hold on, give me 1 second. Let me just do this off screen. Let's see, access to your institution. There are no other options. All right. Well, then, okay. Well, here's the thing. I can't. Well, I don't think I can. Oh, that kind of complicates things. So I can't really show you what the paper is saying. It's kind of a bummer since since it's not open access. I will be violating the policy of this journal. I'm pretty sure there's something that will be violated. So I can't really do that, unfortunately. I will just read in silence, which is usually the goal of my study sessions anyway, to read in silence. But I think today we are going to finish with this. I'm sorry, y'all. But that's what I will do in the next 20-30 minutes. Read this paper. Hopefully this tablet stays powered on because it hasn't shown any weird behavior yet. It got damage in the water. I wish I could show y'all the paper. I really wish I could, but unfortunately, I can't. Who are the authors of this paper? And so this is literature catalysis. 138 absences. What university these folks are associated with? Let's see. Oh, they're in China. Okay. Now I guess that makes sense. A lot of Chinese folks on this paper, on this specific paper. So that's good. That's good. All right. Let me see what's the information again. Nankai University. Nankai University, China. State Laboratory of Fluorine and Nitrogen Chemistry and Advanced Materials, Shanghai Institute of Organic Chemistry, University of Chinese Academy of Sciences, Chinese Academy of Science, Shanghai, China. Let's see who goes. Okay, yeah. So that's where you're located from. Substitution of classical dienes with carbon-carbon bonds in Diels-Alder type reactions is a compelling paradigm in modern syntheses. Through the activation of carbon-carbon bonds, alpha to a single heteroatom has been well established. But although activation of carbon-carbon bonds to a although activation of carbon-carbon bonds alpha to a single heteroatom has been established, extending this strategy to synthetically valuable carbon-carbon moieties, alpha to two heteroatoms remain challenging because of the continued activation of the carbon heteroatom bond. So right off the bat, from last time, we after like a couple of Google searches, we know that activation refers to bond cleavage in this paper. So notes. Let's note this. Bond cleavage. Activation refers to bond cleavage, and heteroatom refers to any non-carbon hydrogen atom. Any organic atom that is not carbon or hydrogen. So it could be sulfur. No, I don't think sulfur is organic. Is it? Oh my god, no, I don't care, like, I need a definition, so if it's not clear, it more than likely is no, at least in the current context. Okay, so activation is carbon bond cleavage, by a metal. Right, okay. So it could be, say, your carbon, and then, so let's say you have this, right, carbon, this H. Actually, then H. OH, right? Where like this is a heteroatom. So apparently, cleavage of a carbon bond to a heteroatom has been a thing for a while, and it's a Diels-Alder type reaction. So I'm pretty sure the reason it's called Diels-Alder is because like it's people discovered it, came up with it, and then they were either awarded posthumously or not. Okay, so although activation of carbon-carbon bonds alpha to a single heteroatom has been well established. Oh, it's not the CO bond, it's the CC bond. Okay. It's the CC bond. Alpha to a single heteroatom has been established. Extending the strategy to valuable CC moieties alpha to two heteroatoms remains challenging because of the competing activation of the adjacent C alpha C heteroatom bonds. Okay. So I see now. So but into I see now. I think I see it now. However, in this instance, we have C double bond. Let's say O H. Actually, I'm just gonna write like this. Let's say it's simple. H C H then H2. I think I'm guessing this has to be some kind of steric hindrance going on, right? When you I haven't looked up how metal activation would work. When I say look up, I mean like the actual mechanism and stuff, right? Because right now, I wish I could show you the paper, but it's literally just showing like a knife, like a scissors coming in the thing around. So it's assuming that you know the mechanism. Which obviously I should as a biochemistry student. But if I were to make a guess as to why this carbon-carbon bond cleavage would be harder because of the competing heteroatom to carbon bond, I'd say it's because of steric hindrance, probably. I'd say it's because of steric hindrance. And hear me out. I think the reason why would be because when you have, and when they say heteroatoms, in this case, they're not small atoms, right? Nitrogen is relatively large compared to like a hydrogen, single hydrogen. When you have, so when you have a larger element on the carbon-carbon bonds are technically shorter because there is strain on that bond, right? I hope I'm not pulling this out of my ass. Holy shit! No. I can't make assumptions. Let's see. Okay. Our carbon. Oh my gosh, I can't type with this thing here. Bonds shorter when they have larger I feel like I got this somewhere. Oh, they tend to be longer. Oh, okay. Wait, alright. Let's find an actual article and talk about this because we need to understand how bond length shapes up with carbon substitution. No, wait, with substitution. Let's see. I need like a. Okay. I need a proper reference. Let's see. Hopefully I can like. Actually, in this case, let me. Alright, let's see. Alright, okay, I can share this with you guys then. Alright, let's look at it, right? Okay, bond order, one child instructed, blah 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 blah. Let's see. So this is an unsaturated bond. This is this is fully saturated. This is unsaturated, and this is the most unsaturated, right? So from order from like least saturated to most saturated, you get shorter to longer bond lengths, right? Let's see. I wonder if this is triple bonds using bonded energy. Bonds between hydrogen and atoms in the same column of the periodic table, decreasing strength as you go down the column. So bonds between hydrogen and atoms in the same column of the periodic table. So I mean, I guess that makes sense because if you're in the first column of the periodic table, you're in metal, and then you are more electropositive as you go down the periods of the periodic table, right? So okay, makes sense. Bonds between like atoms usually become weaker as you go down a column. Note the pattern. Bonds between hydrogen atoms in a given column in the specific periodic table are weaker down the column. Okay, wait. Bonds between hydrogens and atoms in a given column in the periodic table are weaker down the column. Bonds between like atoms usually become weaker down a column. Okay, whatever. Nice information. This is not really what I'm trying to find. Let's see. The relationship between molecular structure and bond energy. Right? Okay, bond energy is defined as the energy required to break a particular bond in a molecule in the gas phase. Pause. Bond energy is defined as the energy required to break a particular bond in a molecule in the gas. Why is it in the gas phase though? So wait, what? Okay, see, like, I mean, this makes sense. This, I don't know. In the gas phase. Why does that have to be in the gas phase? I don't want to go down a rabbit hole. I really don't want to go down a rabbit hole. This is not what I came here for. Actually, screw it. Okay. I'm gonna copy this. Is gas phase. Let's see. Gas phase is specified in bond energy to isolate the chemical bond from any outside forces and neighboring molecules. Okay. So. Okay. I guess like the reason why this is specified is so that when you're determining the bond energy you require to break, you have a more isolated system. Because if you're in a liquid or solid phase, I guess you have more. I mean, it still doesn't honestly. I don't know how that rationale holds when that molecules are more mobile in the gas phase anyway, in the liquid phase. But I mean, I'm not taking breaks. Let's see. By secondary to thermodynamic processes, in condensed states, molecules entirely packed and bound to each other by intermolecular forces like hydrogen bonding. Oh, okay. If you attempt to break this bond, so in a solid phase, not only are you trying to find energy to break the bond itself, but you will be disillusioned because you have to also supply energy to break the intermolecular bonds that are found in solids too. Right? Okay. So that may okay. All right. That was the shortest rabbit hole ever. Honestly, it depends on not only the identity for the bonded atoms, but also let's see. 7:48. I have to go check my stuff in the kitchen. Alright, which would you expect to be stronger? And this is one bonded. Okay, I'm not answering. This didn't really answer my question though. But I mean, then again, if the bonds are longer, I guess it's let's see. Um, so whatever. Let's see. Okay. Anyway, I'm just gonna continue reading this. It's probably here. Right here, buddy. Okay, alright. Alright, that's like the main content, right? So, the Diels-Alder reaction between dienes and dienophiles stands as the cornerstone methodology for six-membrane construction. Building upon this paradigm, important efforts have been devoted over the past several decades to developing alternative annulations using non-diene precursors. Whew. I mean, it makes sense. I mean, let me stop being confident that I think I know what I'm doing. Actually, you know what? It's right. Let me use this break. But I'm gonna go check on stuff in the oven. gotta speed through this stuff. 7:54, 8:10. I'm out. Let's speed through this paper. Well, I'll say speed, but it's really just for this stream. So let's go over this paper, right? These are the reaction between dyes in the NFL stands the cornerstone of biology. I hope this iPad holds up. It's been good so far. Building upon this diagram and building upon this paradigm, important efforts have been devoted over the past several decades to develop alternative annihilation using non-diene precursors. So a diene is, if you think about it, right? Okay. Gosh, like I really gotta. You know what? Let's do this. How about this? Let's come here. Let's do infinite paint here. So, all right. Wait, where's infinite paint? Infinite paint. Okay. So you think about a diene. Just say you have like your organic compound. Let's do butane. Okay. So obviously, since you want to mess with me, right? Let's do butane. Let's come and do this. Do this. So 1, 2, 3, 4. A diene simply means your stuff, your organic compound, has 2 double bonds. Literally, because it's in the di. So when you hear di, it means 2, right? So dibutyl, dipropyl, diene. Add 1 double bond here, and another double bond here. So if I were to guess, this has to be 1, 3, butyl diene. No. Has to be 1, 3. Dibutane. 1, 3 butadiene. I'll have to let me see. Wait, can you not see my stuff? Holy shit. Oh my gosh, it's not even showing. What the hell? Okay, alright. What the hell's going on? Alright. So, what's the name of this? Butadiene. Butyl 1,3-diene. Okay. So this is butyl 1,3-diene, or butadiene. Nice. So yeah, diene, just 2 double bonds. Cool. And the reason it's an ene instead of an ane is because it is double bond. It is a double bond. It's a double bond. All right. Okay. So continue. Wait. Where's this? All right. So what the paper is essentially saying is that there have been efforts to use this so in ring construction, right? If you're doing like a Diels-Alder reaction, you would use a diene. It's for the sake of time, I'm not really going to give you the mechanism and stuff. So what the paper is saying is that there have been efforts to develop a paradigm for 6-member ring construction without using a diene. And why would they want to do that? Well, I mean, possibly because it gives easier chemistry, and maybe it's cheaper, it's more effective. These are just assumptions right now. I haven't fully read into the paper, right? But you can imagine doing this with unsaturated butane will probably provide some benefits, right? So let's say that. Now let's continue reading. Building on this paradigm, important efforts have been devoted over the past several decades to developing alternative annulations using non-diene precursors. And this has been motivated by the potential to expand substrate scope and enhance molecular complexity. Okay, current strategies can be systematically categorized by atom economy principles, which, okay, type 1, bifunctional substrates requiring dual functional group sacrifice. Or type 2, monofunctional substrates expeding one functional group. And type 3, CH activation system with the loss of 2 atoms. Okay. And then type 4, CC bond involving substrates. Alright, okay. So basically, right, let's keep things in track, right? For what you call ring construction, efforts to use non-diene precursors have been pursued. And there are 4 categories. These efforts can be grouped into 4. According to the paper, atom economy principles. These efforts can be grouped into 4 atom economy principles. Number 4, which is CC bond cleavage. So, CC bond cleavage involving substrates. And then in brackets 0 atom loss. I guess it has to mean something. So, from both synthetic and medicinal chemistry perspectives, type 4 substrates offer practical advantages by preserving functional group integrity in ring homologs. Okay, so basically, I mean, this is a rough summary. I could be wrong, but what I'm understanding so far is that by using a CC bond cleavage system, a CC bond activation system, it's probably the least destructive to the atom itself, right? That's what the paper was saying. It said it has practical advantages by preserving functional group integrity in ring homologs. So it's integrity in ring homologs. Cool. So hence the challenge, right? So here's what I'm understanding so far, right? Where's my thing to draw? So like a carbon bond with, let's say, like a Ni2+ plus activation here, like doesn't affect whatever goes on here, right? So like whatever like functional group you could have here, whatever activate, well, not this specific activation, but whatever activation you could give to this bond here to cleave it will preserve this, right? Which I guess it makes sense why that could be seen as an advantage, because if you're trying to make, deliver medication, you don't want to change the shape of the molecule that you're trying to target. That could maybe has like a important structure, right? But that's just speaking like very, very broadly and with a limited scope. But I see the advantage though, and what they essentially as I'm trying to round things up, I think what the paper is hinting at is that if we can do this, we would probably have the best and the most efficient way for constructing ring systems, right? Which could lead to all sort of discoveries like easier syntheses for making XYZ compounds that maybe they were difficult to create or whatever. There are practical applications for this that I could that you could easily think of it, but for sake of time I'm not really gonna go deep in details of it, right? So this makes sense. I guess what you're hinting at though is that doing this while this carbon and this carbon both have heteroatoms is difficult, because if you try to put like if you try to cleave this bond and this is like, I swear to God, this is OH, trust me, this is OH. Try to cleave this bond, but then this has like a hydroxyl group and this has like an amine group. You also then risk cleaving this carbon nitrogen bond or cleaving this carbon hydroxyl group bond, which ultimately alters like the functional group integrity, right? Because you're taking out the functional group, so it's not there. Hence this zinc like system that was built. So that's what it's hinting at. I'm gonna do more study on it while I work during break time, because obviously I have to read and talk about this later. But that's what I think it's hinting at. And hence that system. And since the paper also talks about the practicality of this system, and it seems that beta lactams have a lot of use cases and a lot of medicinal products. And mind, this is why I'm still yet to go do proper research, so don't quote my words here. This is all my assumptions, by the way. Since beta lactams have pragmatic use cases, showing this chemistry on something that is already being used is groundbreaking. Because if the paper is saying, hey, there are practical implications for this kind of chemistry here, and you are already using your established system to cleave, to work your intended reaction, right? Then this is perfect sense. I think I can see why this is a paper in Nature. I think it's because they tried it on the beta lactam and it worked. I don't think maybe if they just proposed this on some other non-functional group, it would have gotten it. But then again, I don't know. These are just very wide speculations, and I'm still a young scientist, so bear with me. But yeah, I think I'm just gonna wrap things up here, this region. I'm gonna come back to this stream later in the evening. I was supposed to do this last evening, but trust me, I was tired from the gym. But yeah, we're gonna come back to this and continue reading this paper. It's pretty cool if you think about it. Right? It's actually pretty cool. But all right, we'll do this later. Come back later, and then yeah, we'll see how things go. I love it.